You having trouble there, Dallas?
No, just opening the coffee.
So this is the kitchen, full commercial kitchen there, but unfortunately the stove's not working this weekend. So we've got everything here in the fridges and who goes there?
Hey, amigo! Oh, thank you.
So there's no gas, eh?
There's no gas, there's no gas.
Listen, don't rub it in. We're so blooming stupid.
I found the gas.
Thank you.
Oh, did you find it?
Yeah.
I thought one of the ladies found it.
No, I found it there. Yeah.
That?
No, we didn't know you had
Who's
to
ever
push the
seen one
button.
of those button things?
We've never seen a button like that.
I mean, I've got a gas bottle at home, you don't push any buttons on the damn
No,
thing.
that's right. You just turn the thing on.
Well,
Say that in our defence.
That's right. They put that on there just to confuse us.
So laugh all you like.
That's
we
right.
will. Ha!
And they let them near telescopes, that's what I'm worried about.
Confusing. How are you two going to run a telescope?
And they're sharing a room, so that's even
We'll
worse.
get it done. It's all cooked. That's right.
This is poetry in motion, I'll have you know.
We're eating very poor tonight, aren't we?
We're very what?
Eating very poor.
Yes, it is very poor. Hey, what if I caught that in my mouth? You know, like in the Blues
Like a
Brothers,
bloody frisbee.
when they're throwing prawns.
Like a frisbee. Sorry about that.
He hasn't got a duster to throw at us.
Just a few talking to technology issues. But we're there. I think we're there. So, this is a presentation that I made to the Astronomical Society at the beginning of the year. Quite a few people here that haven't seen it. Apologies to those few that have seen it. But I think the imagery is such that you're happy to see it now. So this is a visual journey through our solar system. And what we're going to do, if I just check if I can, yeah. What we're going to do is we're going to use the various spacecraft that have either circled or landed on some of the planets, and we're going to pick up the imagery from those and explore that planet with that imagery. What I'll be doing is clicking to videos of say, Mercury, visiting Ceres and so on. But the spacecraft did not take video. These spacecraft don't take video. It's too data intensive and it's too hard to then send back. So they essentially take still images, and they might take one every, depending on the spacecraft and the speed of the spacecraft and what they're doing, what they're trying to image. They might take an image every 10 minutes or 20 minutes, whatever, it depends on the circumstances. And they are beamed back to Earth as separate, they're compressed and then sent back to Earth as separate images. Sometimes within NASA, but there are a number of very enterprising people, because all those files are public access files, and there are some very enterprising people that pick up those still images and with very sophisticated software convert them into a video. And what we'll see is a conversion of those still images, quite often taken well apart from each other, stitched and merged to create a video. So whilst I talk about videos here, they're not actual videos. So that's a journey we'll take. And let's now the other thing is all the imagery you see here is the actual imagery. Every now and again you'll see a slide that says a simulation. The imagery in the background will be correct, but what you'll see is that superimpose the actual spacecraft. Spacecraft can't do a selfie up there, so that's a simulation of the spacecraft with, say, Jupiter in the background. That's what, so this is all genuine imagery.
It's all the big swizzle, in other words.
A big. So let's see. We'll go to Mercury, we'll go to Mars. There was a spacecraft that spent a lot of time around Ceres. There. Then Jupiter, then Saturn, then Pluto. So this is Mercury. So the Messenger spacecraft spent quite a bit of time circling Mercury. This video is solid. Some of the other videos have commentary. This is a solid. And so what we'll do is we'll this. It's pretty clear as well. Yeah. Simulations because they put spacecraft in it, but the imagery is true. These are 3 or 4 minute videos each.
You feel pretty lonely as you saw the Earth disappearing in the background.
So this is Mercury.
I think you could go to Mercury.
And that's the spacecraft.
That's a selfie one.
Yeah, selfies. Yeah.
Selfies. Yeah.
Have you seen the selfies at Curiosity this time?
Yeah.
They're spectacular, aren't they? And you don't see the arm at all.
No, I wonder how they do it. It's
Just
just
a
the
little
way.
trick. No, that's right. No, that's a little trick to it. Bit of Photoshop. Essentially, it takes images from every angle, which is called the arm, and then they Photoshop it out.
It's pretty barren place, isn't it?
Yes, what? Yes, what it is. Well, the other thing is some of these videos, you'll see colour, and they have artificially coloured. Some they've artificially coloured to highlight different topography.
So that looked very wavy, that last look. So why is that like that, do you know? So the craters and it looked really quite a wavy.
So that's been coloured.
That's been coloured to see the different topography. I didn't see that bit. We'll have to go back on.
Yeah, that's okay.
But it's a very barren
Is that a polar cap?
place. No. No. I think they're salts, highly reflective salts.
Have they ever sent back any actual colour photographs?
I don't know what format they've been taken.
What's that stuff coming off the surface there? Did you see on the edge? It's a bit like high winds or something, lying sand or
Some sort of evaporation.
Yeah. We may see it again.
Doesn't have an atmosphere.
No.
So you have all these wisps coming off the edge.
So they found ice, surface ice at the and because there's no atmosphere, if you're in a shadow here and you don't see the sun, it's minus a couple hundred degrees. If you get out in the sun here, it's hundreds of degrees. You go from cold to hot really quickly. And if you're at the limb, because Mercury's gravitationally bound, so it's like the moon with the Earth, it always shows the same side to the sun. So that side is bakingly hot. The other side is approaching absolute zero.
See the wavy?
Yeah. These we don't know. That's for astrogeologists to work out. But this would have been volcanic originally.
That's some video strikes, so and if you see them on the moon, that they spread out.
There's data flows, but you see there were gullies. Mercury's. That's just having a close-up. Last missions now, we have a 50% failure rate.
Wow.
Some of those have failed to get off the Earth's surface, and some have failed to arrive, and a couple have crashed, of course. There are 8, unbelievably, there are 8 current missions at Mars, and quite a few more planned. Now, we're not going to spend time on each of those, but no, there's also, there's ESA, NASA, India, NASA, ESA and NASA.
The Chinese have no doubt coming.
China's coming, the Russians have been there in some of those other missions. And maybe some of these now have come to an end. Goodness knows of curiosity and opportunity whether these will survive that dust storm. And I think opportunity that was already in trouble. Just recently in trouble, so it knows. So all we'll do is just explore one of them, because we haven't got time to go through all of those, obviously. So let's just spend a bit of time with curiosity. And there's a classic selfie with no camera at home. So it's essentially moved its camera around, taken all different selfies, and then they've photoshopped that. So this was launched 26th of November 2011, it's that long ago. Landed on 6th of August 2012. Anyone remember watching that parachute down?
Yes, that was extraordinary.
So this is now video's a few years old. So this is the first 5 years. It's been, as you can see, it's been there a bit longer now. These you can't get a link direct to the video, unfortunately. It's NASA site the way they've got it. I'm always failing to find this. First 5 years, here we go. Probably looks a lot dirtier now.
Well, it's not climate sort of last night, but it was a storm this week.
Quite stunning. Has anyone seen, Sarah? It's an easy spot when it comes into opposition in binoculars, and you can track it moving across the stars. I've seen it a few times. So it comes to opposition once a year. So dawn mission to Vesta and Ceres. Launched, Vesta's easily fine too. Launched 2007, soared past Mars in 2009. 2011 arrived at Vesta and spent 14 months there. We won't look at any of that video. And then 2014 arrived at Ceres. And so it's been circling Ceres, high orbits, low orbits, sweeping in close, going out and sweeping back in. And what we'll do is just have a look at one of the flyover videos of the Ceres. Do you remember the speculation when this was seen for the first time? Do you remember that? No? What is that? So, as in telescopes, all we could see is around, we couldn't resolve anything in telescopes with CERS. But as it got closer, we started to see a disc, and then these popped out.
What for?
There's two eyes popped
Blind
out.
sources.
Yeah, and there's a lot of speculation from scientists about what it was and you know, what did it mean, that sort of thing. As it got closer and closer, what they now believe is that they are salt, because it's been volcanic at some time in the past. They believe these are highly reflective salt deposits that have probably welled up some stones in the past. And because the rest of this is essentially black, and this is a little bit more reflective, they appear as white spots. No chances of us seeing those in our telescopes, but let's...
So is that what they're surmising?
Yes, yes.
Right, okay.
A lot of these projects, they get all this data, and it takes a long time to get the data down, it takes years to analyse it all, and perhaps eventually we'll read somewhere of... which one is that? Who is this one? This is a really good example, as I was saying, of images that have been stitched together to create explores the most prominent craters towards the mountains. There they are for you. So, they've added the background. This is correct imagery, but they've added the background. Simulate them. What they've also done in this video is they've magnified the altitude of the planet, just to see, so you can actually see the. It's hundreds of kilometres across, just hundreds of kilometres.
So those craters pretty new then?
Yes, yes.
So, dummy question, Steve. Where is this in relation to us?
It's in the asteroid belt.
In that.
So this is
Yes.
Vesta and Ceres, the very large ones.
Yes. So it took a long time to get there, didn't it?
Yes. Oh yeah, we're starting to get a fair way out. Okay, let's go to the big one. And let's just spend a little bit of time with Juno. So it's launched 2011, there in 2016, plunged into Jupiter in July 2017. You probably follow that story. This is a video about what have we learned about Jupiter, which was produced a bit before the final plunge, but it essentially gives us all. Apologies for the ads here. This is one of the ones that, this is a commercial one now.
You'll start when you just act marvellous.
Right, woke us up.
On the 5th of July 2016, Juno successfully arrived at Jupiter and inserted itself into a polar orbit. This means Juno has spent the last year gathering data around the biggest planet in our solar system. So what has it actually seen? Was it worth all the fuss of getting this orbiter to Jupiter in the first place? Well, take a look at a few of these breathtaking pictures, and then you tell me.
It's not American.
Of course, Juno isn't just an expensive camera and has been performing several different scientific experiments as well. And the results have completely changed the way we understand the solar system and Jupiter. So what has Juno been doing? It's in a highly perpendicular orbit which brushes over the planet at its closest approach, only 4,200 kilometers above Jupiter's atmosphere. The furthest point takes Juno out over 8.1 million kilometers. Each orbit takes 53 days to complete, and it will complete 12 orbits by the end of its mission in July 2018. At the time of making this video, Juno has completed Perigeo 6, or its 6th closest approach, so we're about halfway through this mission. As Juno is in good health, it could be that its mission is extended beyond 2018. One of the reasons Juno approaches so close to the planet is to avoid Jupiter's powerful radiation belt. There is a gap where the planet ends and the radiation belt starts, and Juno exploits that. There was some concern that Juno would still get a huge dose of radiation from the parts of the radiation belt it does hit, but the radiation was actually 10 times lower than expected in these parts. Great for the health of the probe. Do you remember the previous Jupiter probe, Galileo? Galileo faced a number of setbacks due to the damage received by Jupiter's radiation, as its orbit went right through the middle of the radiation belt. So mission planners were keen to avoid a repeat of that as much as possible. Another advantage of the time distance from Juno to Jupiter at its closest approach is that we've been able to see Jupiter in unprecedented detail. The first images of Jupiter's poles in particular took people's breath away. Some even say that scientists would not have even recognized the planet from these images. Just no one expected what they saw. What you are looking at here are many cyclones around the South Pole. What is remarkable is that the planet looks so different from what we're used to seeing on Jupiter, namely large bands. However, the contrast of the image has been increased to see details. The natural eye would see something more like this. This image is also a mosaic of several images in order to show daytime on all sides of the planet. The North Pole isn't quite so clear as it's in winter and some parts of the pole are in constant night. Juno also has the capability to peer deep into Jupiter's atmosphere using a microwave radiometer, which was designed specifically for this spacecraft. Using it, scientists were able to see the amount of ammonia in the atmosphere. What they didn't expect to see was this band of ammonia around the equator, ammonia being orange in this image. The pillar drops down from the cloud tops over 350 kilometers, the limit of what the MWR can see. Scientists are very puzzled by this, as they expected to see an even distribution of ammonia throughout the planet. They thought the gases in the atmosphere would just mix up, or at least stick to the band pattern on the planet. But these results are far from that. This shows how variable the planet is under the top layer of clouds. Previously, scientists had predicted that Jupiter had a solid core, but using the gravity science instrument, it seems a lot hazier or fuzzier than they would have anticipated. This could imply that the core is not solid, it's dissolved, or it doesn't exist at all. And it may be a while yet until we understand the truth about this point, when all the microwave, radio wave, and magnetic field data have been combined to give a more complete picture. Speaking of the magnetic field, the results from this also came as a surprise to scientists. In some places, the magnetic field was stronger than they expected, and in others, they were weaker. These patches you see also imply that the magnetic field is being generated above the core of the planet, as it's quite irregular, perhaps originating in the metallic hydrogen layer. The magnetic field, as we know, creates aurora, and Juno has an infrared aurora mapper, giving us a view of Jupiter's aurora like we've never seen before. The central band in this animation is the main aurora, and this moving point to the left is caused by the closest of Jupiter's Galilean moons, Io. The tail of the point is the remnants of Io's orbital motion. The whites and greens from this image are ions striking Jupiter's ionosphere from space, and the reds could be ions coming from the planet itself. If this is the case, this has never been observed before. Most of the data collecting takes place only a few hours per orbit as Juno whizzes by the planet. All the instruments collect as much as possible during this time, including the camera. This remarkable video is a time-lapse of Jupiter approaching the northern hemisphere and leaving again as it looks towards the southern hemisphere. And this image is a collection of all the frames that were used in the video. As Juno approaches the planet, you can see the storms around the North Pole, and gradually the view shifts to the mid-latitudes. Zooming in on some of these shots, you can see the classic swirls and patterns we expect on Jupiter. And having a really close look, we can see these white specks. These specks are actually water or ammonia ice clouds, as can be seen by the shadows they create. They are higher in the atmosphere than the rest of the cloud layer, and although they look small, they are actually over 50 kilometers wide. Jupiter is just really big, so it looks small. Now you've noticed them once, you'll start to see them everywhere. Due to the freezing cold temperatures at this altitude where the clouds are, and because they are made of water ice, it could very well be snowing on Jupiter. Remarkably, we are still learning so much about our giant neighbour. You might have thought that because it's the closest and biggest gas giant, we would have a pretty good understanding of its mechanics. It seems with the arrival of Juno, however, we still have a lot to learn, and there's probably questions we don't know yet, let alone answers.
Remember that name? He's got a good YouTube channel.
Well, thank you so much for watching. Your
programs.
support means a great deal to me. I'm sorry for the hiatus. I've been doing a lot of work for uni, but now I have the summer off, and I'm looking forward to getting some videos out to you guys. If you don't want to miss them, be sure to subscribe. And if you want to see more like this, then give it a thumbs up so I know. Thanks, and I'll see you next time.
So that's Jupiter. Let's venture out further where people look. Saturn was a glorious sight last night.
With 25% less sugar and no artificial colours, flavours or sweeteners, they're bursting with fruit flavour.
Okay, sorry. That's the only trouble with it. Okay, let's go to Saturn. We're all familiar with Cassini and the Huygens mission, launched in 1997, ended in 15th September 2017. There's a lot of imagery here. You can go to the NASA site and you can just get an overload of imagery here. I've just picked up two things here. One is just a sort of the wonders of Saturn, a short video just showing the wonders But what I've also picked up is what Huygens saw on Titan, because we're going to get on to Huygens and land on Titan and just have a look. Has anyone seen that video? But, yeah, few have seen it, but not all haven't. So let's take a voyage around Saturn. See, you can go to NASA, any of the sites for any of the programs, we're just going to find this one. You're allowed if you see it.
Saturn Odyssey.
One is a Saturn, here it is. So these are much more civilised. You go here and you don't get all the ads. It's got the spacecraft. So Huygens was the small capsule that Cassini carried with it, and when it arrived at Saturn, in one of the early orbits, it dropped the Cassini probe onto Titan. So the plan was to drop this onto Titan, take measurements as it went down through the atmosphere, and then have a look at, use those cameras on board, have a look at the surface of Titan. So what we'll do is now hitch a ride on that little probe and go down and have a look at the surface. Sorry.
It all starts when you just add marvelous.
January 14th, 2005 begins with the Earth passing directly in between the Sun and Saturn, an opposition so perfect that it occurs maybe twice per millennium. Meanwhile, the Huygens probe, quietly entering the Saturnian system, is about to end its 7-year journey. As Huygens approaches, the inner planets cluster around the distant Sun. Saturn appears almost as large as Orion. A few moons are visible as white dots aligned with Saturn's rings, while Titan, its largest moon, is already well resolved. Huygens is destined for Titan, a mysterious world larger than the planet Mercury and shrouded by a thick brownish-orange atmosphere. the details of its surface have never been seen. Huygens' speed increases to near 6 kilometers per second, and Titan's disk quickly obscures our view of Saturn and its more intimate moons. As the probe enters Titan's atmosphere, the heat shield reduces the speed some 15-fold within a few minutes. The main parachute reduces the speed further. 15 minutes later, the smaller stabilizer chute allows a faster descent at first, but slows as Huygens enters the lower, denser parts of Titan's atmosphere. Huygens is approaching a dark valley between brighter, hilly regions. Beyond the hills to the left, 2 dark parallel lines appear, which are later discovered to be part of a vast system of dunes which surrounds the moon. At 21 kilometers altitude, the probe moves through a thin haze layer as seen on the horizon. The bright area near the center top is the glow of Titan's haze illuminated by the sun. A complicated system of drainage channels, some hundreds of meters wide and kilometers long, are seen cut into the hillside. These are probably the result of runoff from methane rain. Stereographic imagery reveals hills to the left to be perhaps a few hundred meters tall, while features in the valley are tens of meters in height. For most of the descent, the probe travels eastward above Titan's surface. However, below 7 kilometers altitude, the motion reverses into a backward westward motion. It reverses again at 1 kilometer altitude, and we move slowly southeastward. Hang on as Huygens lands on Titan's surface near a water ice outcropping ridge. Another westward-looking view of the descent from 31 kilometers shows the area of Titan over which the probe has just flown. This affords us a good view of the drainage channels and apparent shoreline. More dark lowlands appear and a rough pitted hillside to the left. Spectra of the surface suggest that the bright areas are water ice, and the darker areas are a type of hydrocarbon mixture that has never been produced in the laboratory. The small white dot in the lower center part of scene tracks our progress over Titan's surface. We see the reversal of direction at 7 kilometers altitude, and we fly over the ridge near where we will land. As we approach the surface, our perspective brings the topography to life. We see that although there are rivers and a shoreline, the basin is dry. Below, there are distinct signs of erosion which crafted the rugged ridgeline. Huygens sinks into one of these gullies. We experience a relatively soft landing on Titan's surface. The view from the surface reveals an amazingly Earth-like picture of a dry riverbed with distant hills which are a few meters in height. Some seconds after impact, the shadow of Huygens' parachute drifts across the scene. The heat from the surface science lamp in the probe's skin vaporizes methane from Titan's surface, which is about 180 centigrade degrees below freezing. Near the probe, the ground is littered with water ice rocks and smaller pebbles, which could be made of water ice, or hydrocarbons, or some combination thereof. Although we now know more than ever about this mysterious world, many questions remain unanswered. Where is the vast reservoir of liquid methane necessary to replenish the atmosphere? Where and how often does it rain on Titan? How does the methane get recirculated into the atmosphere? What materials make up the surface? What processes create and shape the hills, dunes, and valleys?
How's that? Fly past Pluto really quickly. So New Horizons, launched 2006, closest point of flyby was the 14th of July 2015. And what we'll do, so this is a series of images that have been stitched together to make it look as though we are descending to land. Of course we don't land because this is a flyby. They had to get everything right here because it flew past Pluto at some amazing speed, 20 or 30,000 kilometres an hour or something, and at a fair distance. So they just had everything lined up, took a series of photographs, and then they just went off in the distance. And it took, so images out here with all the data New Horizons has spent a couple of years transmitting back all the data. It's taken several years to get all the data back, let alone start to analyse it. So this is just a stitching together of all of those single images.
Didn't it have a Commodore 64 computer on board? How long did it take to get to Pluto?
Well,
Yeah, that's right. It's very old technology.
It's 2006.
2006. Yeah, it's very old technology. So
Windows Vista or something.
yeah, probably.
But the other problem was carrying enough energy, and you know, it's sort of the balance between spending a lot of energy to get your data for high transmission back, or drop the transmission rates down, the energy needed, so it could go out and it's visiting another world next year or the year after, and it's going to be the same. New Year's Day, is it?
New Year's Day.
In 19 or?
It's coming.
Oh, is it? Oh, okay. Yes. So it's flying past another object, so it needed to conserve energy for those sort of things. So it's best to just take the time to get the data back. There's, and some of the reading about those surfaces and the young surface is quite an interesting story in itself. One of the things they've been shocked with is how young the surface of the planet is. It's only, I think, only about 10 million years old. That's approach. Shower on the moon, of course. So that's it. So that's a fascinating journey, that one. So it flew past really quickly, and they lined it up carefully so the spacecraft was behind Pluto with the sun behind it, and then it actually lined up and went past Charon and did exactly the same thing. So they could measure get measurements about things for Charon somehow. And then it's gone off. So that's our C14 has played a part in that. There's the C14 out there, as I was mentioning out there, to get those final calculations about where New Horizons should just be aiming to go past Pluto. They wanted very accurate measurements of where Pluto was. Very accurate. And they were able to do that about several months before the flyby. Pluto occulted a star, which was visible here. So the NASA team out here in 2000, must have been early 2015, and rather than bring a telescope out with them, they used that orange C14 and did the occultation measurements here using that telescope. And those occultations were successful. They were clean up, I would say. And those measurements went back to NASA to do the fine tuning of the trajectory for that. NASA and the Planetary Society. Both of those, NASA did so there is just, I mean, you could spend your lifetime. You could be a lounge chair planetary cruiser there, and you never run out of information. The Planetary Society is also a good source of information, and that's it. So we're just
Thank you, Steve.
Who's on next?
Of Scorpius. But this time I chose the most boring constellation. Actually, I was looking at doing Pisces and Aquarius, you know, and I thought, oh, I'll just pick Pisces for now. But actually, just as a quick example of what's up there, because you know this is in the northern sky at the moment, Pisces. So it's ascending, but it's sort of heading up and arcing over. And Aquarius is up above it. But Aquarius is a little more interesting. Pisces has only got one messier object in it.
Hey, that's
so
not...
it's really, as you'll see, it hasn't got a terrible lot. Quick tour. So it's this is a quick tour. So, oh, you can't see a thing here. Can we? Oh, you can't.
It's about as dark as we can make it, man.
That's it, is it?
Yeah.
Cool. Great. Oh, that's not going to be. I can put some chairs in front of that.
Yeah.
Door. Yeah. That's really bad.
It's okay, we'll get a couple of chairs in front of there.
Rotate sideways.
The chair has to come out
A
a
little
little
more.
That all helps.
Bit of aquaculture there. That's good. So, yeah, so this is just maps from both delirium and just quickly, I'll just zero in on what we're going to talk about. So you can see, you know the first point of Aries is now in Pisces, you know it's never but the actual point is shifted over millennia. You know how maps get out of date because of precession, every 50 years you update all the maps, well, you can see it happening in real quick because that point was in a different place. Just a quick example of the what's up there in terms of constellations. Patterns. An interesting one, the fishes are tied together with a ribbon. So this is our constellation Pisces, which is Latin for fish. Cetus, which is a half creature like a goat in the sea with a serpent. Did you know that? People say it's the whale, you know, cetacean, Cetus. But in actual fact, in mythology, it wasn't a creature like a whale at all. Aquarius above it. Anyway, I'll come to a bit of the mythology beforehand. They're just quick examples there of an old map and what it looked like. Anyway, so so there's a story. The constellations associated with a similar story in Greek mythology. I'll just look at the middle one there. The Olympian gods had defeated the Titans and the giants, Gaia, or Mother Earth, coupled with Tartarus. The region of the underworld where Zeus held the Titans imprisoned, and they bred a creature called Typhon. Now, I don't know where the Typhon comes from, but Typhon was this huge creature with many snake heads or dragon's heads, with fire blazing in its eyes. Gaia and Typhon created to defeat the gods. Pan was the first to see this thing coming, so he warned the other gods, and then he transformed himself into a goatfish. And jumped into the river Euphrates, and that's where we get Capricorn, which is right along further. So you got Aquarius and you got Capricorn. So that's just a bit of mythology. The goddess Aphrodite, now here comes the interesting bit, and her son Eros called to the water nymphs for help and jumped into the river Euphrates, trying to flee from this creature. In one version of the legend, the two fishes came to the rescue and carried Aphrodite and Eros on their backs. In another, the mother and son were themselves transformed into fish. Mother and son tied themselves together with a rope cord or a rope or something to make sure that they would not lose each other in the tumbling water. So that's just the story. So what about the interesting facts about Pisces? The zodiac constellation, as you know, so it makes it, it's on the ecliptic. The 14th, in terms of size, the 14th constellation, in terms of area, bounded by Aquarius to the west and Aries to the east, has no bright stars, but is known for some of the larger massive stars. I won't be reading all these notes, I'm just pointing out the main points. Contains only one messier object, and not a particularly good one either. It has 41 stars with 39 known planets, and it has a distinctively shaped, the vertex of which is represented at the point where the mythological ribbons that we just heard about were tied together. The square of Pegasus fits neatly into the space beneath the constellation. I have got a pointer here. If you look up the top, you can see, I have got a pointer. Yeah. that little bit there, see the circle shape? Now that's actually called, and that asterism is called the circlet of Pisces. So it's just a popular thing to look at. But so you can see the V shape quite distinctly if you look at this map. So it goes down here with this particular star we're going to talk about shortly, being at the junction of the two. That's supposed to be another sort of round shape, but it isn't there, just a triangle. Can you see that from back there?
Just,
Now, here are some of the stars. So Ares shows that star there, the top one there, or the second one, up the chord, Alpha Pisces, but it's not the brightest star. So you forget the Bayer designations, Alpha, Beta, Gamma, because they don't actually relate to the brightest stars in this constellation at all. I wonder whether Bayer wasn't smoking something when he came up with some of these things, because over the generations you can see that when they couldn't measure brightness as accurately as we can now anyway, so it doesn't really matter. As long as you know what they are, that's all, Alpha, Beta, Gamma and so on. Yeah, so some of these stars, the interesting thing about these stars is that the brightest is about 3.6 magnitude, and they go down from there. So they're not terribly, it's hard, unless you look for that pattern, it's not a constellation that jumps out at you like Orion does, for example, or Scorpius. You know, which are really
the question, is there any attraction in looking at this particular constellation? Is it anything special?
Yes, I'll come into that. There is one interesting thing in there.
I mean, it's very negative.
But you need a very powerful scope to look at it.
No, Richard's going to get to the end and say, don't bother him.
I'm going to get guys. This is only a quick thing. So, but a lot of these stars are giants. And do you know about these spectral classifications? Does everyone understand these? So that means that's a K-class star. So you go O, B, A, F, G, K, and then M, and then R, N, S, and they've got other sub-classifications and so on. So a K star is really orange already. And then you've got the next number there. It goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 is the hottest, 9 is the coldest. So you can imagine K stars, K0, K1, K2, K3, and then they go down to K9, and they jump over, and they go to M. So M0, 1, 2, 3, like that. But then they've got these other little designations, and they've got tiny little letters, and those little letters mean things like very high metallicity or metal content in the star, or you know, all sorts of weird things. Or strange. One of them is actually strange, strange or odd star. And the 3. Do you know about the so starting at the smallest 3? These are Roman numerals now. So the Roman numerals are at the end. 5, a V, means a main sequence star. So it's a dwarf star, like our sun. So our sun is a 5, classified as a G5, G8V, something like that. So it's a dwarf yellow star. So V is the bottom, then above that is 4. So 4 is a subgiant, 3 is a giant, 2 is a bright giant, and 1 is a supergiant. And then I've got another classification, 0. And that, if you've got a 0 or 1A, that's a hypergiant star. So, but it's not necessarily related to size. It's luminosity, it's the energy output of the star, and so on. So it's not necessarily diameter related, which is interesting. So yeah, so this star here is not far off being, it's bigger than ours, but what is it? Alpha, pouring of the water. So the fish's mouth is at the top. That circle is the fish's mouth. So that's probably the only thing you could recognise, and even then, you'd probably need binoculars to pick out the pattern, wouldn't you, Steve? Have you looked at Steve?
Low power binoculars.
Yeah, we'd probably do it. Could be magnitude 3, 3.5 as the brightest star we can imagine. Most of them around 4, 5, you know.
They must have very dark skies and very good eyesight in the old days.
Yeah.
Dark skies. No pollution.
Yeah.
There are also
And they didn't look at screens.
a lot of yellow and orange stars. And they're not related to each other by distance, but curiously there seem to be a lot of yellow stars in this G-class stars. So that's just a quick example of what's in there. But
Richard.
sorry, you're holding on to your 6 riveting, isn't it? Compared to Scorpius, which I did recently, Scorpius was riveting. This is catatonic. But look, stay away. We just can't. There's a couple of brilliant stories. I've got the data there about the size, and you can see G9. See like the G7. Now I find that curious. There's a 295 lot of 4 light years away for that one, and that's 138, so they're quite a big distance apart. They're still the same. There's a lot of these G-type stars. It must be just common, I think. Being main sequence, I suppose, but the colour, it's interesting, the spectral colour seems to be quite common, at least in this constellation anyway. So I've pointed out a few of them. Van Martin's star is interesting though, because that's a very small dwarf star. With a diameter of 1%, it's a 1% the diameter of the Sun, so it's tiny, but makes it about 8,000 kilometres across, or 7,500 kilometres across or something. A density of 1,000, so a tonne per cubic centimetre, so it's super dense. Third closest white dwarf apart from Sirius B, the partner of Sirius A, the pup as it's known, and Procyon B. So only 13.9 light years away. Can you actually see those numbers that are up there? No, that's pretty fun. Interesting. Its mass though is 68% that of the Sun, so it's very, very dense and very small. And has an age of probably 3 billion years, and it's moving at a fanatical rate at 3 arc seconds per year, which makes it pretty fast. It's quite a big movement. I forget the position angle. 155 degrees. How does that work? Like, you know, if you imagine a clock, 155 degrees, if we use our azimuth system. I mean, does it mean it's going
from due north?
Yeah. So it's using the same system, but it's a 3D thing too, isn't it?
No, that's just...
Is that in relation to what? From where it is at the moment? Yes. In our line of sight, yeah. So down that way. So it's kind of going south-southwest from where it is at the moment. Kulat Nunu, I just like to say that, that's all. This star here, which means the cord of the fish, is another G star, yellow giant star, same sort of thing, also known as Alpha. Now this is what's really confusing. You know, for example, in Scorpius you've got 2 stars with the same name, Alniat, and here you've got one star with different names, completely different names, Kulat Nunu and Alpha, but they mean the same thing. So, you know,
what language is that? What language?
Al-Ferg is definitely Arabic. Anything with Al is going to be Arabic.
Oh, okay.
Kulat Nunu. I don't know. I don't know. Have no idea. Anyway, let's move on. So I just thought I'd point out now. What was the other thing? The chord, a close binary system. Oh, there's nothing else to add there. The spectral class. That's right. So A is sort of like pale blue-white, with more white than blue. The 0 makes it a very hot one. And the P, I think, means peculiar. I'm sure it means peculiar. There's something really peculiar about that star, about the spectrum. So I love the way scientists can do things like that occasionally. It makes it a bit more human and say, this is weird. So deep sky objects now. Just a few deep now. This is where we're, there's not much. So if you go back there, can you see my little arrow to it? M74, which is right next to Kulat Nunu, which is the only reason I'm pointing out Kulat Nunu. So just quickly, that's M74. So it's a nice galaxy. If you
I have, but you can't see those.
Not really.
You need a camera for that.
It's folks, it's the story of Pisces. It's very exciting.
You need to be
even the galaxies are.
The bigger dots he will show.
Yeah.
Will show.
Yeah.
I mean, it has to be visible because it's a messier number, so you can
Yeah,
see.
he must have picked it up.
Yeah, you can see.
I've turned this upside down because this was a Northern Hemisphere production, and therefore now it's in the right orientation. So that star must be that one there, the 3.6 magnitude Kulat Nunu, and that's where the galaxy is in relation to it, because that's 1 degree from there. You can see it's written upside down. So I've turned it up the right way for us, if you're looking at where it was.
With the Messier number of 74, he must have thought it was significant as far as he was concerned. Anyway.
Yeah, it was still visible, yeah. It talks here about having a black hole. It produced a huge release of, what was it? A neutron star appearance of every 2 hours, indicating the presence of an intermediate mass black hole with a mass of 10,000 suns. And up there it talked about supernovae, type 1c supernovae. In 2002, there were 2 hypernovae. Discovery reason is hypernova or supernova explosions with a substantially higher amount of energy than regular supernovae, and I believe to be the origin of long duration gamma ray bursts. Now I suspect that when eddy carotid blows, we'll get the same dose of gamma radiation. It's a very similar situation because that'll be a hypernova because it's such an enormous double star. But the thing is, it could have happened already. You know, I mean, that's 8,500 light years. That's what worries me. You know, we're looking at something 8,500 years ago. Who's to know that we're having a dose of stuff heading our way? Yeah, it's
Well, why worry about it? It's already happened.
Yeah, too late.
Yeah.
We're talking about comets coming on. Now, this is the only exciting thing. Someone said, well, is there anything in Pisces? Well, there is. There's this massive supercluster of stars. Yes, drum roll. And the reason I include this image is because you can see a beautiful example of gravitational lensing. You see these blue? So there are several galaxies behind this supercluster and they're being lensed because the enormous gravitational field, which is actually bent light and improved light, all that sort of stuff, you know, gravity bends light. And so you get this sort of effect. And I have discovered, in a personal way, I worked out where this was. How did I discover where this galactic cluster was? Well, I looked at the longitude and latitude, and then I opened up Starry Night Probe, and I started mucking around with the cursor until it read off the coordinates. Yeah. And because you will never get this, they won't just put an arrow to it. And it's, I reckon the nearest star is TYC1188-, in Pisces. So there it is there. And that's Beta Peg, that little thing there is Beta Pegasi. So it's very close. That's the square of Pegasus is just under here like this. So it's straight under the fish. And it's near that star and very, very close to it. 3 degrees northeast of it. So I reckon that's where the supercluster is. But it's 15th magnitude, I think. Somewhere it's about, and 5.7 billion light years away. So that's the other. So M74 is part of the group of several galaxies, but this one's got NGC 660 being one of them. I'll show you a picture of that. And then there's this big supercluster. But it'd be very faint, wouldn't it? You wouldn't pick it up unless you had a massive.
That's a very interesting image, actually.
Yeah, it's beautiful. It's fascinating to think that's just one of many superclusters. But to finish up, I thought I'd show you the one that's in the M74 group. This is NGC 660. Oh, sorry. No. Oh, that's further on. Sorry, I jumped the gun. A couple of spiral galaxies that are interesting. That one's colliding with 2 colliding galaxies that are visible in this area. But magnitude 12, so moderate telescope and show them they'll be very faint.
Camera.
Yeah, you need a camera to measure these things. This one's a bit brighter. An SAB, I forget how they used to do those what they meant to do with how tight the arms were in the galaxy and those configurations, but a spiral, but it's got a beautiful shape. Unusual. Discovered by Herschel, in this case William Herschel. And that one over there is also known as ARC. Have you ever seen that one, Steve?
No.
ARC 47? No. But we're going to end up a bit like that. One day. When Andromeda merges with us in several billion years. Oh, sorry, I didn't mean to do that. The second last one was the last one. And this is NGC, there it is up there, 660, which is a part of the M74 group that we talked about up there. And that's another pair of blending galaxies that have merged. So they're the only real NGC, interesting deep sky objects there, and the rest of them are so fun. That one there's magnitude 12, and this one discovered by ARC 284, discovered by John Herschel in 1830 up there at the top. So near Corallarino you've got this one, which is an interesting image, and then up here ARC 47 near, what is it, Kappa Pisces, yeah, something up there. But that's it really, there's no... there was
nothing more you can pull out.
A blink.
Thanks, mate.
The Scorpius one is a lot more interesting. There's a lot more to see in Scorpius than there is in Pisces. Sadly, next time we'll do Aquarius.
And does anybody want to admit to being a Pisces?
So apologies for those who have seen some of this material before. This is something that I came across on the net, which I found fascinating, and I started to do something about it. So, how did it take?
If you got one of these, and one of these,
You yourself can detect an extrasolar planet, and I'm going to show you how. So how do you detect an extrasolar planet, a planet around some far-off star, with a pathetic little telephoto lens? If you're very lucky, the planet, as it orbits its star, will come directly in front of the star as viewed from Earth, in which case the amount of light coming from that star diminishes very briefly as the planet passes in front of it. But that signal could be big enough for you to detect with a DSLR camera, and so that's what we're going to attempt to do. The lens that comes with your camera is probably not going to do it, but you can very inexpensively purchase a telephoto like this one. This is a 300mm Nikon telephoto. It's got an adapter which allows me to put it onto my Canon camera. The other thing that you're going to need is some way to get your camera to track the stars as they move through the sky, or I should say as the Earth rotates. You can purchase star trackers. They're kind of expensive, and there's an easier and cheaper way, building something called a barn door tracker. The basic components of the star tracker are all pretty simple. A couple of pieces of plywood, 1/4 inch thick, 1 3/4 inch thick.
This guy's very clever though.
A threaded rod,
This isn't as easy as it looks.
2 threaded rod, gently bent into this segment of a circle with the help of a tree. A couple of gears pulled out of a inkjet printer that was dead. A hunk of piano hinge, or sometimes called continuous hinge, cut from a longer piece obtained at the hardware store, and some very simple electronics, a stepper motor driver board, an Arduino, a switch, and a push button. Initially I mounted my tracker on a tripod, but I decided that was a little too precarious and built a sturdy plywood base for it. Just the tripods and bolts, and a kind of pillar to mount it on here. This angle being the same as my latitude, that helps point the axis of the hinge at the celestial pole. The first task was mounting a stepper motor onto that bottom board. Basically drilling some holes, lining things up, and pressing a gear onto the stepper motor. It's just what's called an interference fit. Basically friction holds it on. The whole thing comes together easily enough. Of course, if you have to build it for the first time and drill all the holes and figure out the design, it takes longer, but here I'm just reassembling it after doing that once.
He gets to the important
The tricky part is putting in that threaded rod, because you got to turn the gear, because the gear that goes around it is sitting underneath the one on top of the stepper motor. You assemble the triangular base, and then you have something to mount it to,
technical gear.
and you're pretty much done. Once the tracker was completed, I could mount my camera on it and take it out at night to remove the trailing that you'd otherwise get as the Earth rotates. To illustrate that, I took an image of the Orion Nebula without tracking, and also with tracking. You see it much cleaner with the tracking turned on. But my target was something different. It was a star called HD 189733, around which there is a known extrasolar planet. The timing of the transit is known, so I took 170 odd pictures at the right time, did something called differential photometry to measure the brightness of that star, and as you can see here in this plot, it diminishes just after the start of the transit and then returns to normal values, thus detecting an extrasolar planet.
Oh, that's very clever.
When they did the stargazing live on the ABC, people had found those exoplanets. Quite a few.
Just by studying the
Yeah.
data.
Well, that's how they just went out and variable stuff.
Okay. This will just be very quickly. As you know, I've been mucking about with astro imaging for a few years now, and after a break for a while, I started to take it up again. And these are some of the images that I've been taking from Opossum Bay at South Arm here in Hobart. There are some from Sydney as well, but this will give you an idea of what can be achieved. This was taken with that 90mm telescope that you see outside there. So I include this just to show you that you don't need a whiz-bang Takahashi to take a reasonably nice and pretty image. That's a 90mm scope. It's taken with a colour camera and with stacked images.
Beautiful.
Okay. I'm also very keen on hot globules. So this is the running chook, and this is the stellar factory here, which I'm very interested in. Now these colours, you can't see them all that well here, but this is the Hubble palette. So this is taken with a mono camera, with colour filters, HA, sulfur and oxygen, and you map the colours to what's called the Hubble palette, and you get these extraordinary colours, which bring out the different gases. So the white one here, by the way, is oxygen, and the greeny one here is hydrogen. So by varying the colours, you can do various things. So here again, you can see I've varied the colours again, trying to delve and get closer into this block globule here, which is where they believe stars are born. Deeper, and you can just see here. Again, colour. And you can become quite artistic. You can sometimes take it too far. Look, it depends, whatever floats your boat, really. Some people find that pretty, some people find it garish. Then also I had a go at the Pillars of Creation, which was made famous by Hubble. I'll show you some comparisons there. So this is Hubble in 1995 with the Pillars, and that's a more recent photograph that they've taken. They've enhanced it and they've got better optics, and you can see there's been quite dramatic improvement just with the Hubble imaging. And so those are my pillars. Oops. And can you get a little bit bigger? Okay, so it's not Hubble, but it will take some magnification. I reckon for a little 5-inch telescope from a backyard at South Arm, compared to $2.1 billion, I was very happy.
You've got the job.
Well, it took them a while to get it right, too. Okay. Then what else? Okay, occasionally, now this is a comet that I took some time ago. That was taken with that same 90mm telescope out there. And what else have we got here? 90mm telescope, again, with a colour camera.
Did you use an extender for that, Rich, or?
No, that was cropped and enlarged.
Sure. And was that with your?
That's 90mm.
No, the camera. I mean, was the?
That was a colour camera. That was a colour camera.
Yeah.
Okay. This is Takahashi. I do have a presentation actually. You can't see it all here on focusing and how important it is to focus. As many as you know, the challenge with a globular cluster is to separate the stars in the core, and also to show the temperature changes. Now on my screen I can see that this is quite white and this becomes quite orange, which is as it should be. And also as you enlarge this, you actually can get some separation. And that's what you're after. So I can still see some separation here. So I was fairly happy with that guy. So if you get in, I've also got a vivid imagination. I thought to myself now, what would happen if these are all suns, so they reckon originally they thought there were 1 million suns in this globular cluster. They've now recomputed this and they reckon it's 10 million suns. And I thought, well, if you were on a little guy on a planet orbiting one of these these suns, and you looked up at the night sky, what would you see? I mean, it'd be mind-boggling.
Actually, Richard,
Yes.
from one of those, you wouldn't get a night sky.
No, you wouldn't. It'd be daylight, yeah.
It would be like
Yeah,
twilight, I imagine.
Yeah,
but
that's
read
right.
quite comfortably.
That's dead right. Okay.
Because they're only half a light year apart or something in the setup. Can you imagine?
Okay.
It's nothing in space.
Right. Okay. Takahashi. So that's my sombrero. That's 35 million light years away. Okay. And what else? Okay. So this is hydrogen alpha. And this will actually take some...
Is that the running chicken again, Rich?
No, this is the pillars. This is the pillars. Yeah,
Oh.
okay.
Is that hydrogen alpha only?
Oh, yeah.
Yeah, hydrogen alpha only.
Yeah.
So you can actually see it actually takes some magnification. Now this is with the TAC. And that's at 1,000 millimeter native focal length.
The eagles will become a chicken.
Yeah, that's right. Okay, and then of course you get the usual suspects. We've all taken this. It's a pretty little object. And yeah, and a little bit closer. So there'll be just something else I'll show you. Okay, so that's more recent in 2013. Yeah, there was just one last comparison and then we'll call it a day. There's one other thing I wanted to show you. It's there. Yeah. A lot of people say, well, you know, what is your setup at home? So this is how I used to do it, including the cat, which would always play with the wires in the spinning telescope. I really miss that guy. He was great. He used to be out there at 3 o'clock in the morning, keeping me company. So this is the 90 millimeter that you see outside there.
Is that William Optics?
Yeah, that's William Optics.
That's the 90.
Yeah, that's the 90, and that's on Takahashi now, that's the EM200.
That's exactly what's out there at the moment.
Yeah, correct. Yeah. And so some of those images were taken with that telescope.
That's an SB, is it?
Okay, that's the EM. Okay, that's the EM400. So that's the bigger mount, which I've got in a small observatory. And this is the sort of setup that I've got at the moment in my backyard. I'm very fortunate.
That's the coolest thing.
That's it. Really, you know, I'm up and running within about 3 or 4 minutes. Look, it took me a few years to save for that, but it was well worth it. And that's made in America, and it's made out of plastic. It's the same polyester material that they make kids' playgrounds out of at McDonald's. Same sort of stuff. It'll never wear out. These wheels around the side here are skate wheels from inline skates. And that's how you just move it around. Very, very clever. Give you an idea of size. So size, okay. There you can see that that's the size of the thing in my backyard. So
2 kids in the playhouse.
you
3 kids.
yeah, that's right. That's my one. I came around with a filter wheel and everything.
That's STL 8300.
Yeah, 8,300, and you can just see the robo focus. Electronic focusing is essential for this sort of stuff.
And the SkyX will run that too, won't it?
Oh yeah, well it does. It does. And I think that sort of concludes. I've got bored. I think we're ready for a siesta now.
That's fantastic.
Thank you very much.
Well, here we are at Orana Beach Camp, long weekend, and we've got 25 members. So we've got absolutely beautiful weather the last night and tonight, absolutely crystal clear, as you can see by the sky. I'm just going to go around and introduce some people and tell us about their telescopes. Richard, would you like to tell us a little bit about your setup, please?
Yep. So the mount is a Takahashi EM200. It's a nice light portable mount. And on it I have a small refracting telescope, which is a Williams 90 millimeter. It's called a Williams Migres. And then at the back I've got a color camera, an S-Big color camera. And we're hoping that the wispy clouds disappear and we can do some astrophotography tonight.
Excellent. And that's driven by SkyX, wasn't it?
Yep,
I'll
Sky.
just go behind you.
Yep, SkyX Planetarium software.
Thanks, Richard. So how's it going, Dallas?
Ah, going really great.
Looking forward to tonight and tomorrow?
Yeah, I've got my equatorial mount and the Dob set up, ready to go.
Oh, very good. So what do you got tonight? You got the...
I've got a 10-inch Dobsonian over there, and I've got a Celestron 9.2-inch Schmidt Cassegrain set up on an equatorial mount.
Very good. Well, that should be a good night tonight.
Yeah.
After we have our feast.
That's right.
Oh.
This is Richard, another Richard. You can tell us a little bit about your setup.
He's just pulling faces.
No, he's not.
This is my beautiful triple APO refractor from Germany. It's a 152mm, very 1200mm f7.9 triple APO. And it weighs a ton, but it has very nice images. Delivers very nice images. Sitting on top of a Skywatcher mount, a Skywatcher AZ-EQ6 GT, and I'm really excited. I've got it lined up and ready to use with my laptop tonight for some guided observing using the SkyX Professional program, and hopefully we'll see a lot tonight.
Thanks.
Looking forward.
Here we got Steve Harvey, Vice President of the Association. Can you tell us a little bit about your setup?
Well, refractor, Vixen 5.5-inch refractor from Japan, an eyepieces with a T-Rex mount, which I can use for star hopping manually, finding things, or around here is an Argo Navis for computer guided finding objects. We've just in the middle of the day had a good look at Venus, which is a pretty jewel crescent, almost like a ring with a bright blue background and this white sparkling ring, which is very pretty, very pretty.
Excellent. Yeah, and the tripod?
So this is actually a surveyor's tripod, a Mizox surveyor's tripod, made of wood, which wood is probably the best material for tripods because it dampens any vibrations. Nice and strong.
Thanks, Steve.
Thanks, mate.
We've got Michael Booth, he's from Launceston.
Hi there, this is my solar imaging, my solar viewing setup, and I've got a Coronado PST, which has a hydrogen alpha filter, and plus just a regular plain white filter on an Orion Shorty telescope there, just to add both views. We've been looking at the sun this afternoon, a few small prominences and a couple of little filaments there of interest, and I've got a lighter weight Skywatcher HEQ5 mount here, which is just perfect for on-the-go imaging and travelling. And hopefully tonight it's going to behave when I try to align it.
Yeah, another perfect night.
Yes.
Thanks for that, Michael.
No worries.
Alan?
8-inch Mead, Smith Cassegrain. About 40 years old. Works well now. Driven by a battery.
And good old reliable.
Yeah.
Yeah.
8-inch.
Thanks, Alan.
All right, Michael, tell us about your setup, mate.
I'm the guy that's usually on the other end of that camera. I've got a Celestron Edge HD 8-inch on a Skywatcher EQ6R Pro, the new ones with the belt drive. I've got the dew heaters on here, extra weights, and also got the weights on the front here because of the weight on the back with all the cameras later on tonight. Got the Orion 60mm finder scope, and also on this side I've got the red dot finder.
Yeah, you won't get it with that.
put this together myself.
I just want to see if there's any.
All the electrics are in the box down
Yes,
here.
look at that on the limb there,
So
on the
I've
right.
got
That's
the,
superb. Have a look.
I've seen it before, battery chargers and everything all goes
I haven't
through,
seen
and
them
the
actually.
USB link in there.
Little,
Oh, sorry. There you go.
little adapters.
So everything's locked away in there, so I just pack it all in and all
screw
fold
them
up,
onto
and that's
the
driven
eyepiece
by
and then you-
SkyX
No,
That's about it.
Thank you, Michael. That's a nice setup.
Oh, okay, so you're not...
Pity about your shirt.
I'm Rose Wright, and I've got a Skywatcher Pro series on an HEQ5 Pro mount, which I got second hand, so I don't really know what I've got, and I'm just learning how to use it. But last night I got it lined up and tracking, which I was very pleased with.
And you're the only one went swimming in the cold water today.
And it wasn't even that cold.
Thanks, Rosalind. So you're trying to get Venus again?
Yes.
Okay.
Hi, I'm Gareth. I've got a Skywatch reflector tube 200B Dobsonian telescope, or Newtonian telescope on a Dobsonian mount.
And how long you been interested in this hobby?
For about 3 months.
3 months?
Yeah.
Excellent. Yeah, very good.
Looking forward to taking some photographs tonight as well.
Well, we've had our best 2 nights for many years, so yeah, hopefully. Thanks.
Alright, I'm David. I've got this 8-inch Dob. I've been interested in astronomy since forever and only just recently decided to do something about it. So here I am.
Oh, excellent. Well, we've got a good night tonight, so yeah, and terrific. Here we go.
Okay. Hello, I'm Peter Scully, and I've got a Bintel 200 reflector telescope, and I've been interested in astronomy for many years, but only getting serious in the last couple of months, which I've been a member of the association. We're here at Lauderdale on the most wonderful weekend camp, and the weather's been kind to us, and we're all having a wonderful time, and particularly for beginners like myself, I'm learning an enormous amount thanks to the help that I'm getting from everybody else. Anyway.
Thanks, Peter.
Thank you very much.
Very good, thanks. Okay, go for
Have
it.
you got the telescope? That really jazzy one?
It does, yeah.
That one. Oh, look, that's ours.
It's Jackie and John, yeah. Very good.
It's a fantastic night.
That's good.
Good night.
It is, yeah, nice and sunny, and it's been our best one for a while, so yeah. All right, terrific. Here we go, mad breakfast time. We've got the cook there. So how's it going, Chris? Going all right?
Yeah, going well. Yeah, the man just keeps growing.
There's the lady that stood up all night.
2:30.
2:30. You got you've got the telescope bug. Oh, this is Roaches Beach, so we're only about 3-minute walk from where we were. And that was the weekend, till next year.